Hi, everyone. Let's take a look at section 2.4. It's going to show some of the applications of this logic we've been learning in the field of computer science. And so we're going to specifically be just looking at some simple digital logic circuits. So we're not going to dive real deep into this topic. We're just getting a basic understanding for how the logic will apply to the computer science field and creating circuits of information. So we're going to learn about black boxes and gates. So we know that signals in computers are sent through bits of ones and zeros, and we can transform them into other combinations of ones and zeros by means of a circuit. Let's see, because of a variety of different technologies that are used in circuit construction, computer engineers and digital system designers find it useful to think of certain basic circuits as black boxes. Okay, so we have a black box where some stuff happens inside the black box. Okay. And so often it's ignored if where the attention is focused on just the relationship between the input and the output signal. So here we have three input signals, P, Q, and R, and one output signal, S. And so some logic happens in the black box. The operation of a black box is completely specified by constructing an input output table that lists all its possible input signals together with their corresponding output signals. So, for example, the black box pictured has three input signals. And since each of these signals can take the value of 1 or 0, there are 8 possible combinations of input signals. Now, does this table ring a bell? It certainly should, because it is so similar to your truth table. You can think about the ones as being true and the zeros as being false. And so, no surprise that with three inputs, a P, a Q, and an R, there are 8 possibilities for all of those. And now we don't know about the logic that's going on here. So, this is just one possible list of outputs for S. So it says the third row, for instance, indicates that for inputs P equal 1, Q equals 0, and R equal 1, the output S is 0. All right, so that's a little bit about black boxes. Let's talk about gates. A NOT gate or inverter, it's a circuit with one input signal and one output signal. If the input signal is 1, the output signal is 0. Conversely, if the input signal is 0, then the output signal is 1. So you can see why it's a NOT gate or an inverter. It simply changes the value that is entered into the circuit. So it just reverses it, it negates it, if you will. We also have AND gates and OR gates. So an AND gate is a circuit that's going to have 2 input signals and 1 output signal. Now, if both input signals are 1, then the output signal is 1. Otherwise, the output signal is 0. Now, again, think about the connection to these circuits and the logic we've been studying. And means both things are true, or both things have a value of 1. The OR gate has 2 input signals as well and 1 output signal, but you only need one in order for the output to be 1. So if both input signals are 0, then the output signal is 0. But otherwise, the output signal is 1. So we only need one of the input signals to be 1 or the other. Okay, this is a nice little table to demonstrate the not, the and the or gates. Take a look at the tables. I'm just going to let you kind of look at this a little bit. If you need to pause the video and kind of study what's going on with the not, the and the or gate. Notice that the not gate acts like the little tilde, where R is simply not P. Okay, you can see that if you're looking at the output for R, it's simply the negation of P. So this would be similar to our little tilde representing not. All right, so we have in the AND gate P and Q. Again, in order for R to have a value of 1, which you could equate to true, both P and Q must have true values, or a 1. All other possibilities result in a 0 output. All right, for the OR gate, we only need P or Q to have a 1. The only time that the output is 0 is if neither P nor Q have a value of 1. Here are a few general rules for combining circuits. Never combine 2 input wires. A single input wire can be split partway and used as input for 2 separate gates. So while you don't want to combine 2 inputs, you can split an input. An output wire can be used as an input. So once a wire is an output, it can be input into another circuit or box. No output of a gate can eventually feed back into that gate. There's a note here that last rule might be violated in more complex circuits, but we're not going to worry about that here. All right, so if you're given a set of input signals for a circuit, you can find its output by tracing through the circuit gate by gate. Okay, so here we have a circuit. The input signals are P is 0 and Q is 1. Okay, so think about tracing our way through the circuit. So if P is a 0 and Q is a 1. Now, once the 0 goes through the NOT gate, it becomes a 1. And so what's being input into this gate, the AND? We have a 1 and a 1, and so the output will, of course, be 1. So the output R is 1. Let's take a look at this next example. We have our circuit. The input signals are P is 1, Q is 0, and R is 1. So let's work our way through the gates. So with the OR gate, we only need one of the inputs to be 1. And certainly since P is 1, then one or the other is 1. The 1 travels through the NOT gate and becomes a 0. And so what's being input into the AND gate is a 0 and a 1. Now remember, in an AND gate, in order for the output to be a 1, both inputs must be a 1. Since they aren't, then the output is 0. So S will have a value of 0. Again, I encourage you to pause here and kind of think through that logic. Okay, so this is just explaining what I just did. If you want to read through that, you're welcome to. This is explaining our second example. It says construct the input-output table for the following circuit. Okay, so now we're looking at all the possibilities. Okay, so one of the inputs, it could be P is 1 and Q is 1. Or maybe P is 1 and Q is 0. Or maybe Q is 1 and P is 0. Or maybe they're both 0. So you look at all the possibilities, very similar to a truth table. And since it is an or, remember the only way R will be 0 is if both inputs are 0. And so you can see, well, that's not, oh, sorry. I forgot the not on the Q. It's like, wait, that doesn't look right. So whatever input happens for Q is going to change here. So if a 0 enters this gate, it will turn into a 1. So you can follow through. I would encourage you to start with your input and then see if you can go back to this gate and logically deduce the output for R. Okay, I don't know why this slide is kind of messed up, but it's basically talking about something we call Boolean variables. A Boolean variable is simply what we've been talking about, where there is only two values that the Boolean variable can take: true, false, 1 or 0. And so when you see this word Boolean, it is talking about those types of things where a circuit could be, we could have a 0 or a 1, a true or a false. And we know that that is the basis for computer information. It says find the Boolean expressions. Basically, these are going back to our logic expressions. And so when we deal with these in the field of computer science, you might see them referred to Boolean expressions, but they're really just our logic statements. And so what we want to do is write an expression based on what we see here. So notice that we have, I kind of like to work backwards on this, okay? We have an and, so I know that there's going to be an and. Okay, so then I can work on the left side is P or Q. So what is this? This is an or, P or Q. All right. The other side we have a not. If we trace back, there's a not. And then there's an and statement. And the inputs into the and box are P and Q. Okay, so you can see that looks very similar to the logic statements we were finding earlier. So you don't have to work backwards to create these, but for some reason it just makes most sense to me. So again, this one ends with an and. And so on the left side, I will look at the first input into and, which is also an and statement. It's P and Q. Okay, P and Q. The other side is I encounter a not and then R. So you see, you can work through the gates and the wires to create your Boolean expression. And so they're kind of showing you that. I don't know that they worked through it backwards, but for some reason that just tends to work best for me. I'm not sure why these slides are kind of messed up. And there's that second example. Again, if you want to pause and take a look at that. Okay, so we have another type of Boolean expression called a recognizer, and it's a circuit that outputs a 1 for only one particular combination of input signals and zeros for all others. So you can think of it as recognizing that one desired possibility. So if you look at this example, you can see that this is a recognizer. If you look here, there's only one possible combination where we're going to get a 1 or a true, you might think. So this is maybe where the signal would be turned on and then off in all other instances. So it's trying to recognize that one special circumstance. Okay, so we've looked at some circuits and created Boolean expressions. Now, what about if we have the Boolean expression and then we try to create the circuit? Again, I might kind of work backwards. For example, I see I have some stuff or some other stuff. So I might start with my OR gate, all right, and then work backwards from there. So I know I have an OR. I'm not going to worry about the shapes of these. And so one side is another. So when I look at this part, I see that it is an and. So I've got an and. What is the and? I have a Q and I have a not P. So I need a not circuit and then P. And then the other side of this OR is a not Q. So I have another not circuit and Q. Now I know that's not exactly beautiful, but you can kind of see at least my design here. Now in this next example, I have 3 things coming into my and. So I might begin with my and. Okay. I've got 3 things coming into this. So I've got, I've got T coming in here. I've got another and statement, R and S. R, S. And then I've got another, I see I'm reading this wrong. Let me start over on this one. I missed a set of parentheses. Okay, so let me start over here. Okay, so I see that this is all in parentheses. So I have all of this and T. Okay, so let me do my and the T is here. Then I got a bunch of stuff going on, this other input. I have an and. Okay, and so 2 things are leading into the ands, which is 2 more ands. So I have an and with P and Q. And I have another and with R and S. All right, so just a little rough, a rough draft of what the circuits would look like. Okay, and you'd be happy to know that on a test or quiz, I have not asked you to draw your own circuit, simply to recognize one or at least be able to follow the logic through. So here's one that looks really nice. Or this one also looks nice. Okay. So here it says consider the 2 combination circuits, and we're almost done with this. And the idea here is that this left circuit has the same logical input and output as the one on the right. And so why would we go through all of this if we could just do this? Okay, that's one of the jobs sometimes of computer analysts and programmers is they try to find ways to save memory, to save time. And as you can imagine, the circuit on the right is much more efficient in terms of computer time and memory and all the things. If you trace through circuit A, you will find this is its input-output table. Okay. And if you trace the one for the other one, you will find it is exactly the same. So we have an equivalent equivalent table. These both have the same input-output table, so we have equivalent circuits. So simplifying circuits, again, it takes up less space, requires less power, and so often we try to find ways to simplify circuits if possible. Okay, a couple more gates to talk about, NAND and NOR. So it's sort of a combination of the NOT gate and the AND gate, okay, and the NOT gate and the OR gate. Okay, so it's kind of a combination gate. All right, so the NAND gate, it's a single gate that acts like an AND gate followed by a NOT. So we'll take the AND value and then, of course, negate it. A NOR gate acts like an OR gate followed by a NOT gate. So it will find the OR value and then switch it. So the output signal for a NAND gate is 0 when and only when both input signals are 1. Okay, the output signal for a NOR gate is 1 when and only when both input signals are 0. So again, you may have to pause and kind of run that through your brain to make sure that makes sense. Okay, we have a couple of logical symbols that correspond to these gates. This vertical line here stands for NAND. Okay, so and then not. So it means this. It means not P and Q. And then this symbol here, this down arrow, it stands for NOR. Okay, so we have a Sheffer stroke and a Pierce arrow. And so the Pierce arrow, it means not P or Q. So you may want to make a note of those. Again, this is not a huge part of the course where you won't see these circuits a lot. But I did want to introduce them to you so that you can see some of the connections between the logic that we are learning about and the field of computer science, because they are most definitely very strongly related. All right, so you could kind of take a look at this table to see how the NAND and NOR gates work. So I'm not going to talk you through this, but take a moment, pause the video, and kind of reason through this so that you see how these two particular gates work. And that's it. I hope you enjoyed this section and its application to the logic that we've been doing. So best wishes to you.